or we're going to look at worksheet 7.4, problem number 2. Find a Taylor series about x equals 0 for the integral from the integral of e to the x squared over x. I couldn't even do a u sub on this. I couldn't do integration by parts. It would create that loop. And so therefore we have to do something using Taylor series on this. So let's start with what we know. And I know there's bounds on that, or there's boxes for bounds. That was just the notation for this particular program. So let's start with what we know. We know that if I'm dealing with e to the x, this would be the series from 0 to infinity of x to the n over n factorial. Okay, and if we plug in e to the x squared, we get this series that looks like this. And again, if we then do e to the x squared over x, we get the series n equals 0 to infinity of x to the 2n over x times n factorial. Cleaning that up, we get the series from n equals 0 to infinity of x to the 2n minus 1 over n factorial. Okay, so if I were to expand this, I'm not going to do the integral just yet. I just want you to watch. If I were to expand this, what I would get when I plug in n equals 0, we would get in this 1 over x, and you can check the math on that one. If, you know, it might be better if I do it this way just so you can see the pattern. We would get x to the negative 1. We would get, when we plug in n equals 1, we would get x to the first over 1 factorial. When we plug in n equals 2, we would get x cubed over 2 factorial, and this pattern continues. And I could keep going. Okay, so if this is what we expanded it to, this is what we'd get. Now the rule says that if we're going to integrate this, which is what the whole point of this problem was, the integration of this should be equivalent to the integration of the whole thing. Okay, so if we watch this integral, and I'm going to do this in a different color, but if we watch this integral right here, let's do this, and I'm just going to change it to a gray. I would go up a degree if I integrate this. So I'm going to go up a degree. So this would be x to the 2n over n factorial times 2n, right? So go up a degree, divide by that degree, n factorial. Now, if I integrate the parts of it, the expansion part of it, I would go, this would be the natural log of x plus, this would go up a degree, and I would divide by that degree, but I already have the 1 factorial. I know that seems silly to write, but you will be able to see the pattern here in just a second. I would go up a degree here. I would divide by that degree, multiplied by what was already there. I'd go up a degree, divide by that degree, multiplied by what was already there. Okay. Now, what should happen is when I substitute in my n here, if I were to expand this, I should get the exact same terms. So expanding this by plugging in n equals 0, when I plug in n equals 0, I get 1 over 0. That's not defined. This is undefined. Now if I plug in 1, n equals 1, when I plug in n equals 1, we would get x squared over 2 times 1 factorial. And if I plug in n equals 2, I would get x to the 4th over 4 times 2 factorial. And if I plug in n equals 3, I get x to the 6th over 6 times 3 factorial. So there's a couple things happening here. These terms match up. My problem comes from this term right here. If I take the antiderivative of the expansion of the series that we had here, we get the natural log of the absolute value of x. If I expand what was the antiderivative, I get a term that doesn't exist. I can't have it both ways. I have to have the series the same either way, and it's not the same at the moment, okay? So because it's not the same at the moment, except for what happens down here, I'm going to take this idea and I'm going to rewrite it. So instead of using this expanded part right here, or instead of using this whole thing, what I'm going to do is I'm going to separate it. I'm going to separate it into the one term that was causing me problems and then all of these other terms. Can you think of a way to rewrite all of these other terms here? So if I were to think of a way to take these terms and rewrite them, all of them, wouldn't you agree that that expression right there would really just be the sum from n equals 1 to infinity of that x to the 2n minus 1 over n factorial? Isn't that that expression? That's the expression that we're going to integrate. But I also am going to add to it this expression here. Let's do that in a different color. I'm going to add to it this expression here. I need to account for that. So this is just going to be 1 over x, or x to the negative 1. So really what I'm doing is I'm going to be taking the integral of both of these parts. Okay, so I don't know why I just raised that. The integral of both of these parts. That's what I'm going to be taking the integral of. So the 1 over x, the integral of 1 over x, is the natural log of the absolute value of x plus c. And then the integral of this series is what we got up here, just the index has been shifted. So this will be from n equals 1 to infinity of x to the 2n over 2n times n factorial. And that's how we expand that. Now the question is asked, how do we know? How do we know we can't just go write this, which we're getting pretty good at doing, and take the antiderivative? Well, the issue is we may not know this just looking at this expression. It's in taking the antiderivative and looking at that bottom term. Usually where there's the only place where there will be a problem are at the endpoints. And since at n equals 0, we get something that's undefined, that is where the problem lies. So if you take the antiderivative or you take the derivative and you get an expression that yields something that's undefined, you need to go back and rethink your series. Expand the original series and say, okay, what patterns do I see? What should I get? I should get this expression here. What I did get was this expression. Okay, these match up. This one doesn't. So I need to take this piece, this x to the negative 1, separately. And I hope that helps explain the answer just a little bit better on that problem.